Thank you for joining this webinar today. I'm very glad of being here today. This is a great opportunity to share these projects made in Universidad de Antioquia in Colombia to the Capella community. So, well, as Martin said previously, my name is Paula Andrea García. I am an aerospace engineer from Colombia, and today, alongside Juan Felipe, we will be presenting the use of MBSE for space system design using Capella. And for me, well, my project is the design and development of a vacuum chamber POC for a modular space vacuum chamber. Well, so I think that we can just get it started. So, well, this project focuses on how model-based system engineer can help structure complex space system architectures and how it can support early design decisions. But first of all, before talking about models, about tools, it is important to understand the whole context. And this is like one of our main questions. Why does simulation facilities matter? And why are the vacuum chambers important for space systems? So, well, space systems cannot be fully tested in real conditions once they are deployed. You have to do it here on Earth. So simulation facilities, they play a critical, extremely important role through the entire life cycle of every space project. So vacuum chambers, in particular, they enable, for example, material qualification, mechanism testing, sensor validation, and even the more bizarre testing or space testing that you can think of. For example, kinetic impactor simulation for lunar exploration. So although these facilities, they are ground-based, they are facilities here on Earth, they behave, or they try to behave like really complex space systems themselves. So yeah, they are multidisciplinary, they are safety critical, they are intended for long-term reuse, and of course they are expensive, really expensive, but they have a lot of applications and you can do a lot of things with them. And they, as I say, they are intended for a long-term reuse. This project in particular is an agreement between Universidad de Antioquia, my alma mater, and Orbital Mining Corporation, an American startup. So this is like a little bit of context. And now we can go to the the model-based system engineer and Capella side of the project. So this is where MBSE engineering becomes like particularly valuable. Model-based system engineer allows us to do a lot of things, but it especially allows us to reason about, for example, the system using models rather than disconnected documents. So this allows us to make relationships, to make dependencies and assumptions in a very explicit way. So Capella, together with the Arcadia methodology, provides a clear separation between the operational system, the logical, the operational system, logical, and physical architecture concerns of our project. So this structure is especially well suited for complex infrastructure system, or in general with complex systems. So where in this complex system, the understanding of the interactions and the responsibilities are very important, but they are just as important as defining all the components of your project or your system or your, in this case, facility. So for the project overview, for the vacuum chamber for space systems testing, the whole objective, the main objective of this project was to develop a proof of concept for a modular vacuum chamber that is capable of simulating space-like conditions. This mission, defined at system level, was to operate vacuum chamber and space simulation. But rather than building the chamber, the goal was to produce a complete and a consistent system design that is ready to support future construction, future integration, service provision, and including experiments such as lunar impactor simulations, or, for example, software testing simulation, and well, so on. So here is like our bridge into modeling. For this project, we started at the operational level. We focused on understanding the problem before proposing any solution. And this is a very important lesson in my university, specifically at our space engineering. We have this problem. We started very early trying to propose solutions for any project, and we let aside like the part of trying to understand really the problem, the project, and obviously it led to not so good results. So then we met with this kind of design process, and it really helped us a lot. So using the operational architecture, we identified all relevant actors. In this case, the user, the operator, the maintenance technician, the IT administrator, the safety supervisor. But we also modeled the vacuum chamber as an operational entity interacting with these actors. This step helped clarify responsibilities, constraints, interactions during normal operations, maintenance, and abnormal situations. So, well, at this stage, clearly we do not have technical solutions, and we do not have technical solutions defined. We only have operational needs and interactions. Well, for the operational scenarios and the functional chains, these were used to describe how all the activities unfold over time. For example, like a simple example, running a vacuum space simulation involves preparation, system initialization, evacuation, experiment execution, data acquisition, safety monitoring, and so on. So these functional chains that we see here revealed hidden dependencies between the actors that were defined and highlighted the safety and control critical interactions early in the process. So this information directly influenced later architectural definitions. Now for the system architecture, this like bridge between the operational architecture to like some early solutions, we based everything on the operational analysis. So we transitioned to the system and the logical architecture. So here we focused on what the system must do, independently of how it will be implemented. The main thing was how what is the system is going to do, what the system must do. So we defined our system. It's the vacuum chamber, how it relates to all of the dependencies, and well, we defined a lot of capabilities. So here we have the CSA, the contextual system actor diagram, and on the right side we have the mission capability diagram. The key system function, such as, for example, vacuum generation, experiment control, data acquisition, safety management, they were identified and they were then allocated. This naturally led us to a logical decomposition into systems that we can see in this slide. This logical decomposition led us to a subsystem definition. The subsystem definition includes vacuum generation, control and automation, safety management, IT and communication, and data acquisition. So let's get back a little bit. This is a mode state machine diagram that we did. This is just a very simple approach to the natural flow that the vacuum chamber should do. This may seem too logical, too easy to understand, but it helps us a lot because, well, you have to think step by step all the process that the vacuum chamber has to do when it is going to like start and run on a specific test. And it also helps us think about all the things that can go wrong. So we can analyze them and we can try to do a lot of early decisions in in the architecture of the system that can support all the future construction or definition of the system. Well, this is the general system logical architecture. Well, we defined a lot of subsystem, but we can do like a detailed diagrams. For example, here we have the vacuum, the whole vacuum chamber system, but we have, for example, the vacuum generation subsystem, and how it has another subsystem inside it, and how all of these subsystems connect and interact with all the other subsystems of the vacuum chamber. Here we have another example without functional chains. It is the control and automation subsystem. Well, now we have the physical architecture. In the physical architecture, logical functions were mapped to real components and nodes. This is one of my favorite parts of the whole design project, because we have to start thinking about all the physical components of all the physical objects that you have to then procure or buy for construct your facility. So, well, this physical architecture includes a lot of things like vacuum pumps, valves, sensor, PLCs, operator consoles, safety devices, etc. Here is a little bit bigger, so you can see it a little bit more. A lot of physical links and component exchanges were modeled, and this allowed us an early identification of critical nodes and interfaces. This step supported a lot of early trade-offs related to integration complexity, costs, without yet committing to final detailed designs. And well, now here I present the EPBS. This diagram, this component item breakdown diagram, helped us identify configuration items. So here we distinguish between COTS, or components of the shelf, custom hardware, and software elements. So here we are like in the state we say like, okay, we have all of the design process. We have take all the things into account, and now we have to separate all of the things that we have to, for example, procure or integrate or validate. So, for example, if we need to do custom hardware, we are going to place it here in this diagram, and we know that then in another stage of the process, in another stage of the design process, we have to establish like time or money or whatever to do the development of that custom hardware. Or if we just have to buy it anywhere, or if we have to develop another software, I think that you get the idea. This was the last stage of this project. As I said at the beginning, the project was intended to do a proof of concept or for a design more than construct the vacuum chamber itself. But overall, model-based system engineer through Capella provided much more than diagrams, that much more than a lot of diagrams. It really enabled us full traceability from mission objectives, from capabilities to physical components. It supported safer early decisions. And it resulted in a modular and scalable architecture for a vacuum chamber. And most importantly, the system model itself becomes a reusable asset. It will support future evolution of this design. It can help upgrades and new services. So what I've shown is how MBSE can be applied to design the infrastructure that enable a lot of space capabilities, space activities on the ground here on Earth. But the same principles, the operational clarity, the functional decomposition, the architectural traceability, are even more critical when we move to mission-driven space systems. And that transition from simulation facilities to operational missions is exactly what will be presented by Juan, Felipe, with the application of model-based system engineer to near-Earth object detection.
So, first question to Paula about the end of your presentation. How long the model take to develop and how many people were working on it? Did you have a lot of engagement with Orbital Mining to develop the model, or was it developed independently? And if there was engagement, how difficult was it to map their ideas into an MBSE model? Thanks in advance from Aaron.
Okay, thank you for this question. The model take around 5 months to develop. It was it was like a project to obtain my degree at Universidad of Antioquia. It was an agreement with Orbital Mining Corporation and my university. And how many people were working? Well, to be honest, I I did the whole model with my internal professor, Juan Francisco Puerta, and another of my professors at the university, Diego Francisco Hidalgo, and also with the help of my assessor in Orbital Mining Corporation, Chris Dalton. But well, honestly, I did the model. It took around 5 months, 5 to 4 months. I have experience with complex ideas or complex space-like projects, and modeling them into Capella, with Capella, because a lot of the subjects in my university teach this. So, for example, I have to do like another 2 projects with Capella during my school years. So I have like the experience. It was a little bit difficult because this is like a facility. So it's an object. It's not an idea. It's an object. So maybe that part was a little bit difficult for the first stage of the design project. So the design process, sorry. But for example, for the physical architecture or the EPBS, it was easier because it's something physical. It's not an idea. So just think about all the items that you have to buy or something. It was easier. Yes, I think that will answer the question.
So the question is, for organizations that have already implemented matured own MBSE methodologies based on SysML, how do you recommend positioning Capella and Arcadia as a front-end MBSE tool without creating methodological conflicts or duplicated modeling efforts?
In my case, for Orbital Mining Corporation, they haven't used methodologies based on SysML. So in my case, it was pretty easy to introduce model-based system engineer for this project specifically. And they were pretty open-minded about this. And as soon as they saw the facility or all the good things that MBSE brought to a company, and like the fast pacing that you have for all the projects with model-based system engineer, they were very glad that I introduced it to the company. For organizations that have already implemented another methodologies, I think that maybe they can start with projects that are not huge, that are not critical for the company, so they can do like a little try. They can give it a try and like organize the methodologies that are going to use for each project, so can reduce the conflicts or the efforts on each project. That's like just an idea that occurred to me right now.
So next question. I see that there is a rapid vertical transition in the slide story flow from an operational artifact to system level one, then to logical, physical ones, and end product breakdown structure. I believe that in the Arcadia workflow, it is envisioned the work is decomposed, left to right, prayer advancing top down. Thus, the question is the work presented rapidly like this due to time constraint allocated for the presentation during the webinar? Or do you propose that the architecture analysis and design could be done like this?
Well, yes, absolutely. There's a time constraint in the presentation. I do not do the top to down process. I did follow the Capella workflow, so I didn't like present all the other modeling process here because of time, but I did follow the Capella recommended workflow.
Which resources would you recommend to learn Capella Arcadia for complex space systems? Because most of the literature I found has only very simple examples, which are good to get the idea, but are not directly applicable to complex systems, like in his case, a satellite.
This is true. We have this issue at my university because we we did all the projects space oriented, in a space oriented theme, and all the most of the examples that are available for Capella are not in this industry. So, well, for example, now this kind of spaces like this webinar can help to fit a little bit more these topics for Capella and Arcadia methodology. But to be honest, we try to compare all of these examples to the area that we are in. And I think that this is the perfect opportunity to try to improve these kind of examples about modeling space systems related. And another thing that helped us a lot, besides the official references that Capella brings to us, is the Capella forum. Sometimes I have like a very specific question about like a modeling idea for a specific diagram, and most of the time there were someone in the forum answer my question. So those places like the forum and the webinars are pretty much a good help in this area.
Okay, great, thanks. It's always a good question to see how people, what people use to get familiar with Capella. Why did you use the Arcadia method and not other methods such as OPM?
Well, I did use the Arcadia method because, as I said, is one of the methods that are teach at my university. But mostly because the traditional methods, like the document drive methodologies, engineering methodologies, are pretty complex. And we are already trying to develop or design a very complex system. So a very complex system and then another complex methodology. It's a big problem. Also because I was like time restricted, I had to do this project in around 5 to 6 months. So Capella and the Arcadia methodology has a pretty fast design process. Also, Capella is a multi-level operational form or way to model all these systems, and it helps us to visualize even for the physical architecture or for the procurement process. Also, for with the Arcadia methodology, we can have a lot of detailing during the process, and also we have a lot of traceability. And there's a thing that I really like about Capella and about this methodology, and is that you are like doing your model, and you always can check if there's anything that you left or that you forget about. And because of this style of methodology, you can just like assess this problem and then you can go and try to correct it. But it will reflect on all of your diagrams. It will reflect in all of your model process. So that's fantastic. You don't have to like work a lot around a problem, a mistake, or something you forgot. So you can just correct it and then just go on with your process and with your design process.
So, okay, let's go to the next question. Can Capella provide complete traceability from requirements to architecture to implementation, design, and test specification from Dennis?
Yes, it can provide it. And that's one of the reasons that I used Capella for this specific project, because I had an idea. I had all the requirements. I have a specific stakeholders. I have a cost limitation. I have a time limitation. So it was a very good way to understand all of the requirements, to identify all of the requirements that I have, and then try to translate it to this kind of methodology, to the model. And for example, for the architecture, for the physical architecture, it helped me a lot. pretty much. And for example, the multi-state machine that I showed in one of the slides, it was a pretty good tool to understand all the workflow of this kind of facilities.
Thanks, Paula, and thank you to everyone for joining us. My name is Juan Felipe Ríos Orozco, and as Paula said, now we are going to focus in other type of applications within the space field. In this case, from a mission design perspective, and of course, with the systems design, which in this case is a space-based observatory for NEO detection. I would like to start with the definition of NEO, a near-Earth object. Near-Earth objects are asteroids or comets whose orbits have been influenced by the gravitational pulls of nearby planets, mainly by Jupiter, because as you can see, most of them comes from the main asteroid belt. And those gravitational effects allowing them to come close to Earth's orbit. Technically, you consider this type of objects a NEO if they have a perihelion distance of less than 1.3 astronomical units. One astronomical unit is approximately 150 million kilometers. What is the alarming fact? Asteroids larger than 140 meters can cause regional damage, and only approximately 40% of them have been detected so far. And it's even more alarming that smaller asteroids can generate great damage too. And you can see that if they are smaller, the population of those asteroids or asteroids mostly that have been detected is really low. Well, yeah, there are many limitations with ground-based observation, as you can see here. Atmospheric interference due to weather conditions, reduced field of view, and detectability of news coming from the sun's direction. That is the target of this specific observatory, those news. And with space observations, we have benefits such as increased coverage, absence of those atmospheric interferences. And the main advantage in this context is that we have the capability to observe areas close to the sun, which are impossible to observe from the Earth because of the effects of the solar radiation into the sensors. So there are two main entities in this context. The aerospace engineering, that is the engineering entity, and the science institute entity. The engineering entity is responsible for all the design, for the operations, and the design of the mission in general and of the observatory. And the science institute is responsible to provide scientific goals such as the population of news that we want to detect, and in general, many requirements about those specific characteristics. And with the operational architecture, it was important to make this mission design architecture because when we are designing a mission, it is relevant to understand all the stakeholders and all the entities which are involved in the mission project. Of course, always the space will be present because it provides the operational conditions. And of course, we have the operational architecture at the operational level. Here we start to see two main functional chains, in this case, the neo detection and target track is selected. It's important because when the Science Institute provides us the need to detect a specific object, the observatory shall to have the ability to detect it. And this operational analysis also implies other analysis. In this case of a space mission, the astrodynamics aspect, there are many possibilities to select the operational orbit, but these specific points are Lagrange points, which are the result of circular restricted three-body problems, which is where we have the gravitational effects from two main bodies, and it provides specific zones with specific families of orbits, very interesting for many type of applications. And the selected point for this operation is the Lagrange point L1 because it provides a good observational coverage for NEOs approaching from the sun direction, which here are represented in the red zone, favorable phase angles, and easier communications compared to other options. Now, at this level, we are thinking about the different configurations for future phases, and we have to consider, for instance, how will be the design for the specific subsystems. I mean, we are not talking about subsystems yet, but if I know that if I select the wrong point for the observatory, I know that there will be issues with many components that we will see later. And the spectral range selected is the infrared because in that range, we could take advantages such as that we could detect NEOs with asteroids with low albedo, which are impossible for the visible range of ground observatories. And because we could get different characteristics, such as the diameter. Here you can see the operational orbit. And with the modes of operation, this is important because it's close to a CONOPS, because here we have the different modes that the observatory will have, starting from the pre-launch operations and until the decommissioning operations. So as you can see, we also have different choices nodes that where the observatory have to select yes or no option, and according to that answer, it remains in the same mode or it goes to other mode. This is very important because it also provides constraints to the system, because we have to consider all the operational constraints. And also it is important because we can make like a zoom in each mode, in this case the nominal operation that represents the operation when the observatory is detecting a NEO, from the attitude determination, changing the orientation of the observatory, and the preparation of the instrument, the capture of the images, and finally with the data storage, and again that process. And now with the system analysis, we have the observatory as a black box level. We start to analyze the different functions that it must to have to achieve all the goals with all the functions related. As you can see, there is always present the NEO detection functional chain and the target tracking selected. And we start to analyze different interactions, in this case of as a function level. And this analysis led us to understand what will be the subsystems. In this case, we have these subsystems that you can see here. And an important aspect of this phase is that we can import in Capella requirements file. And this is very, very important because in that way we can guarantee the traceability of each requirement in the way that we can allocate each one to the specific subsystem that is related to each requirement. So here we can see the logical interactions between subsystems, but because we are talking about a complex system, it is very necessary to understand internally how works each subsystem. So here we have a system to subsystems transition that is very useful in Capella. And as I told you, with the requirements allocation to each subsystem. And this is relevant because it also provides the logical functions, because there are different types of mechanisms and configuration that we can select for each subsystem in a space systems. So according to this analysis, we can later select the correct components in the physical analysis. So as you can see here, this process was made for each subsystem. And the physical analysis, now we have specific components, as Paula said, and physical interfaces that are very important, because now we see how are those relations between the different subsystems, but in this case with a specific physical interface. And the same is the same process. We made the physical analysis for each subsystem, physical architecture. It's very, it has a high level of detail, as you can see here. For instance, for the thermal control, we have the specific components such as the sun shield, because the infrared instrument always must be protected from sun rays. And the mechanism for the thermal management, in this case, is a cooling mechanism with radiators. And as you can see here, is attached to the hot element with high purity heat straps. And it's the same process with all the subsystems. We did with that level of details. And now you can see the payload that is the infrared instrument. So here we have all the different interfaces between the main components, as you can see here. And this is also thanks to the previous operational analysis. So I think that for space mission, that operational analysis is very relevant because, as you can see, the selection of the operational orbit provide different constraints that we have to consider in the selection of different components. And finally, for the scope of this work, there is no possible whole validation and verification process because we will have to make a rigorous process with many components and with component level. So here is just a short analysis for evaluation and verification with some tools such as GMAT by NASA and other models in Python. And GMAT led us to propagate the orbit. So here we have the orbit. As many of you could know, the validation is related to answer the question if we build the correct system, and verification is related to answer if we build the system correctly. So in this case, we can validate the selection of the orbit because here we can see that the observatory is always following the L1 point and pointing to the sun's direction, but also each requirement must be verifiable. So in this case, we have some requirements about, for instance, propulsion subsystem. And now in that way, we can verify the need of a propulsion subsystem because we have to realize different orbital corrections. So in that way, we can also verify each subsystem that is each requirement, because that's necessary for a good systems engineering process. As part of this same validation process, in the tool, we could analyze the observation window times. In this case, you can see that we have one window per day, and for some missions, it could be enough. But in this case, because we are talking about planetary defense mission, we have to maintain direct contact all the time with the Earth. It was a mission requirement. So with just one ground station, it was not possible, as you can see here. So in that way, we could validate that with networks such as the NASA Deep Space Network, we can achieve that goal, that requirement about maintain a constant contact with the Earth if the observatory detects something and if it has to report it to Earth. And thanks to everyone for joining us.
How would you realize a transition from a spreadsheet-based approach towards MBSE if you're already in phase B? For example, would you still do an OA and SA and use it to refine the results you already got, like preliminary functions and architecture? Or do you think this will produce more overhead than benefits and start straight with modeling the preliminary functional and physical architecture that you already have defined?
Well, MBSE provides a very useful approach, and is that all the process is iterative in the design process. Actually, I had that case because in advanced phases of the design, it's normal that we can find some mistakes, or we have to change something to in order to make it something easier for a specific subsystem to achieve a requirement. So Capella provides us that possibility to make an iterative process. And actually, if the transition between the different analyses are made correctly, if you change something in for instance, the operational analysis, if you change it, you can see the changes into the next analysis. So that's a very useful function provided by Capella.
Well, I think I will answer what would I do in this case. If I have like an advanced approach for a project, but in a spreadsheet methodology, I will try to start again in Capella or with a model-based system engineer approach, and I will try to compare both methodologies. If you have time, if you have the time or the capabilities, or you have the time mostly to do it, I would recommend to do it, like, and then compare the results, and then you can try to know which one is better for your project or for the kind of design that you are trying to do.
Okay, great. Thanks for the answer. So this is the next question by Jim Adams. So have you heard of the CubeSat System Reference Model, or CSRM, from OMG and INCOSE? It's currently instantiated in SysML in Cameo, and there's interest in instantiating in other languages and tools.
I think Martin probably knows more than me in this aspect, but I understand the Capella, the basis of Capella is also SysML, like 70% SysML, I think. I'm not sure, Martin. But yeah, of course. Yeah, sorry, please.
No, sorry, just on that, it's, let's say, the Arcadia modeling language, it's inspired by SysML, very
Yeah,
strongly
Arcadia,
inspired by
sorry.
SysML, yeah, but it's not really technically directly compatible with SysML. So in that instance, it would have to be a new implementation, for example. So yeah, it was just to add on that, but you can continue.
Yes, because with the Arcadia method, we are focused more on the architectures, and for these specific projects, we found that the design in the architectures, it was very useful. Of course, it will be interesting to make the transition to other languages, because I know that with SysML we have other types of diagrams, but yeah, for the purpose of these projects, in this case, we found very useful the Arcadia method for the architectures.
Yeah, well, I haven't heard, unfortunately, I haven't heard of this CSRM by OMG and INCOSE, but I will give it a look. It sounds pretty good, and as Felipe said, it's pretty good. It's something that you wished for. Know another languages and another methodologies and a lot of tools to try to do this design process.
And of course, if there can be reference models implemented in Capella, that's also great. And actually, let me move back. There's one question that isn't in the file, but I see we marked it as answered by mistake. So I'll come back to this one, which is Nepal, because I see it has a lot of votes. So I think it's better if we answer it now. This being said, it might be more of a question for Obeo and myself than Juan and Paula. I don't know what you think, Juan, Paula, but if you have things to say about it, go ahead. Otherwise, I'll just answer that. So the question is, with many organizations actively preparing for SysML v2 and API-driven ecosystem, how do you see Capella evolving to coexist with SysML v2 based toolchains over the next few years? So yeah, since it is a question about mostly the Capella roadmap, I think it's more a question to Obeo, and what I can say about it for now. It's that, yeah, that's a good point, and we're already working on that. And so at the end, Capella will converge, or the current idea is that Capella will converge into a SysML v2 tool. So that what might happen at some point is that Capella in one of the next coming releases at some point will become also based on SysML v2, and Arcadia will be implemented on SysML v2. So there is work on that to make Capella and Arcadia converge into SysML v2. Thank you, Juan and Paula, for presenting your work. I think it was very interesting and well received by the audience and the community.
Bye, thank you so much.
And thank you, Martin.
You're welcome. Thank you, guys.